yesterday through, I would say, somewhat advanced discussion. We came up with a motion equation for an object that looked like this. I think that's what it looked like, right? And as an equation goes, there are a couple of features here. This is based on the idea that a coffee filter is being dropped through the air, is going to experience drag, and there are two forces acting on it, mg and cv. I wanted you to figure out what the position function looked like. And what I'm finding is that there's some difficulty with the mathematics. So before we tackle this, and just to be clear, I know I've heard this from a couple of you. I don't care where you are in A, B, or B, C. Okay? Or not at all. This is the reality of what we need to do. So we need to learn how to do this. Consider this your calculus instruction then. Here. To figure out x, I have to replace v with dx dt. Now, what I'm really supposed to be doing here is taking the integral. Although we talked about the word antiderivative, really taking the integral. And to do that, I've got to find a way to make this look like things I've done before. Now, the truth is, this constant is way out front. It's not going to matter. Meaning, if I write this as dx equals mg over c times 1 minus e to the negative c over mt dt. I'm really just integrating both sides. Now that looks really, really hard. So let's make it look smaller. Let's make it look easier. First, the integral acts like any operator. It can be distributed. It can be factored out, stuff like that. The first thing I'm going to do is take this constant and move it away from everything. Put it all the way out front so it's not even a part of the problem. Then I'm going to break this up into two integrals. And I'm going to focus on just one of them at a time. This is a polynomial, so I can do this. A polynomial just has different terms that are added or subtracted from each other. So I'm going to focus on that first term. And just that first term, which is the integral of 1 with respect to t. That 1 is actually t to the 0 power. So I will add 1 to the exponent, divide by the new exponent, and that term is done. I'm going to try and recognize in the next term that all of this is my C value. So 1 over all of that times the original function, and that's that term. Now I'd like to clean this up. So the first thing I will do to clean it up is distribute the mg over c. I'm going to reciprocate this. So that's negative m over c. And then finish up with that. This is x as a function of t. Now, most all of this was calculus. There was very little by way of actual physics here. But this is kind of my expectation. You'll have to be able to do this. Now, when we're done here, this looks really, really complicated. But this term here is the terminal velocity. That's really all it is. I know we see it twice. That's okay. The reason I bring it up is, do you remember this? Does that look familiar? I wrote it there because this part is what would happen if there was no acceleration. And this part is what gets added to it if there is an acceleration. If you rewrite this, as complicated as this looks, I've got a part that exists if there's no acceleration, and a part that exists because of the acceleration. What's funny about this is at time 0, this is 1, and the whole thing is governed by this term here at time 0, because this term goes away at time 0. After a long, long, long time, this term becomes 0, and this becomes what's left over. Which is why when we talked about this right in the class yesterday, although some of you were packing up, we were talking about the coffee filter lab. And how when we looked at the position versus the time for the coffee filter, we used the graph to measure the velocity. You got a graph that looks something like this. This was the part where it was accelerating, and this is the part where it had a constant velocity. I'd like you to see this. So in your calculator right now, I want you to graph this. Go. Same thing, I just factored out the mg over t. Okay? Just upside down, right? And I want you to get accustomed to graphing this. Let me write it all back in here. All right, there you go. That's what it looks like, right? That's the function from a minute. All you need to plot is what's here. So in your calculator, just to get the shape of the plot, do x plus e to the negative x. Get rid of all the extra stuff there. All the extra stuff just moves the graph around a little bit. All you want is the shape of the graph. Now, your graph isn't going to look like what I just drew, but I do think your graph is probably going to look, and we're only interested in the first quadrant, something like that. It's the same graph. It's going away from the origin, not towards it. You guys follow that okay? I know it's a little glacier slow, but let me, I even hate to do this, but I'm going to. I'm just trying to put it all in one place for you. Isn't that it? All we've done? So if it looks like any of these things, and if they're just added together, you should be able to do it. Is that too fast? Reverse of this is true. I'm sorry. I could also, of course, I have to keep going. Is that enough? Just a reminder of the things we know. Your job is to make whatever function you have look like this. Just so that there's an opportunity for a clean look. Let's talk a little bit about the function e to the x. All right. The derivative with respect to x of e to the x is just e to the x. That's the weirdness of it. Now, that suggests, though, that you could have d dx of, say, e to the c times x. Now, specifically, if you were asked to do this, you are supposed to use what's called the chain rule. And the chain rule would allow you to figure out what this derivative should be. And for those of you who know what the chain rule is, it's kind of like substitution, but for derivatives. So what you would kind of do is say u equals cx and change this to d du of e to the u, while at the same time computing du dx. Over here, that would give you c, because the derivative of u when u is cx with respect to x is just c. Are there any questions about what I just did here so far? So to get d dx, we're going to take d du times du dx. So let's figure out what this part is. d du is just e to the u. So when I put these together, I get e to the u times c. Substituting everything in, I'm going to get c e to the cx. Now, there shouldn't be many surprises there. The vast majority of you have done this, but some people in the back are stretching the c. We good? Okay. So that suggests that I want to use it. d dx of e to the cx is just c e to the cx. Someplace in your notes, if you are a calculus novice, begin building your own chart of different derivatives, just so you have a point of reference that you can go back to and check to see how to do some of these. You don't need the whole story. I don't know why I have an equal sign here either, sorry. You don't need the whole story, you need this. Now, there's going to come a time where I'm going to ask you to take the derivative of something that might be relatively complicated. Like all of that. When we did this yesterday, I know. But you need to see that this is the function that's here. That's the hard part for you guys. Seeing inside of all of this mess and understanding that this whole mess is just e to the cx. In the case of the thing that's out front, it's a constant. You can just completely disregard it and take it and move it out front as if it's not even there. And then you need to recognize that all of this has suddenly just become c. So that your result has the thing you pulled out front, the thing that represents c, and the result of taking the derivative. Again, the hard part is seeing the root function. Through the complex portion. Now, here, have is a bag of tricks. A set of tables that tells you how to handle different types of derivatives and integrals. And I'm going to tell you right now, you should have one. You should be able to do this now. Because I'm going to need you to do the reverse. Meaning, I'm going to need you to be able to find the antiderivative of this as well. Now, as stated, this is just e to the x plus a constant. Now, for those of you who are in AB, you're going to have trouble with understanding why this constant is here sometimes and not here other times. So let me kind of elucidate you as to why the constant appears here sometimes and not other times. If I had put in limits to my integration, And actually, let's make this a more straightforward integral. This. Without the limits, you guys have already been taught that the answer to this would be 1/2 x squared. I don't believe I have to express that, where that comes from, but that I should place a constant here. In this case, a constant that represents the initial condition of the problem. Now, the reason why this constant doesn't exist when I put in limits is because when I find my antiderivative, even if I was to put a constant in there, the constant won't be present after I put in my limits. I'd have 1/2 b squared plus c minus 1/2 a squared plus c. So whenever limits are employed, the constant will be subtracted away. So for those of you in AB, that's why you'll see the constant appear sometimes and disappear others. I only have to worry about the constant if I don't have limits on my integration. We're going to have limits on all of our integration, so we should be okay to not worry about the constant too much. But we still have to deal with this more complex problem. You're never going to have e to the x. You're going to have e to the cx. Now, the truth is, to figure out what this integral is, I'm supposed to use u substitution. But I'm wondering if you can't reason together what the answer should look like by just reversing the process we did. Is it too much for you to see that the answer should be something like that? For you guys in AB, that's what I'm really targeting with that question. And the reason I'm saying that is because if the derivative of e to the cx gives me c e to the cx, then when I work backwards, I'm going to be dividing by this to get rid of that c out front. Thus, it should look like that. But also, to see how it should be done, I can do u substitution. Everybody okay so far with what I've done? I can do my u substitution now. Factor out the 1 over c. Form this integration. Substitute back in my u sub. All right, follow those steps, because what I want